So last time we talked about diagonalization, talk about finding the value of a matrix. We want to continue. I understand many of you already learned this in other classes, but it's good just to review, okay? So let's talk about matrix diagonalization, okay? So let's say I have a matrix. Now let's go to a very general form. This matrix is an n by n matrix. So what are the elements? A00, A01, all the way to A0n minus 1. Okay? And then we go down. This is an minus 1, 0, an minus 1, 1, and then all the way to an minus 1, n minus 1. How many columns, how many rows do we have for this matrix?
N by
N.
N.
Thank you. So this is a n by n matrix. So as we said, the matrix is determined by its elements. If I know all the elements, I know what this matrix is, right? So there's a shorthand form. Sometimes we want to refer to the element. I can just say this is the matrix Aij. What does it mean? It means its element this means that this is the element of of the ith row, jth column. So you need to also follow this convention. The first index is the row, the second index is the column, okay? That's what we use in the class and in most textbooks and most places, okay? Any questions? So I say I have a matrix Aij. Basically, of course, you get no information, but you know that the elements are labeled as Aij. So I can talk about this matrix or its element by just referring to Aij. And I runs from 0 to n minus 1. J runs from 0 to n minus 1. Okay? Okay, so this is our matrix. And then I also want to say, okay, and then we also assume A lambda I equals to lambda I. If I tell you lambda I is a scalar, then what is the meaning of lambda I, cat? What's the meaning of lambda I? It's a vector, but can you be more specific? What is the eigenvector of A, and this is the eigenvalue of A. If I can write it in this way. Okay? Right, so I'm repeating, I know, but you need to be very familiar with this, right? So this is eigenvector of A. This is the eigenvalue of A. Okay? Now, then I say let. If this is an eigenvector, whether it's eigenvector or not, I can write it as this, alpha 0 all the way to alpha n minus 1, right? For any vector in this space, it has n values. Do I make any mistake writing this as a column form for this vector? He say no. I also think no. I have n elements, right? Alpha 0, alpha I, alpha n minus 1 can be some complex number. Okay? Then what does it mean if this is the case? Then I try to apply A to it. A lambda I equals to A00 all the way to A0n minus 1, right? I try to only write the corner numbers. n minus 1, 0, all the way to a n minus 1, a n minus 1. This whole thing times alpha 0 all the way to alpha n minus 1. Right? When I say a lambda equal to this, a times lambda I, then it's just this matrix times this vector, right? Any questions so far for this notation? We need to be very familiar with this. Any questions? Please help others if you have questions. When you ask, some people don't ask questions, right? If you ask, you're actually helping others. Any problem with this notation? Oh, good. Okay. But then we also say what? We say because it's the eigenvector, then we also have lambda I times lambda I, right? And this lambda I is just this, right? Just a number, alpha 0 all the way alpha n minus 1. Right? I just substitute with the column vector. Now, just want to pay a trick. I want to show you that this is also equal to what? Because this is just, if I do multiply, this is just lambda I alpha 0 all the way to lambda I alpha n minus 1. Is this okay? When we multiply a scalar to a vector, all the elements will get multiplied by that scalar, right? Now this one I also can obtain as what? This is the same as something like this, lambda I, diagonal lambda I, and then you have 0 everywhere times alpha 0 all the way to alpha n minus 1. Do you see that? Because for the first row, it's lambda I times 0, right? So it's only alpha 0 times lambda I. The last 9, everything is 0. So it is, you do the multiplication, it's just lambda I times alpha n minus 1. And this is diagonal. So for each of these terms, we only receive lambda I. Make sense? Can you see this? Any questions? So, but this is nothing but just equals to lambda I times an identity matrix, and then times lambda I. Now, I could have just said this at the beginning. It's really, I mean, taking you around, just tell you something trivial. But I want you to appreciate this multiplication and the relationship between the elements. Of course, you know lambda I times lambda I must be equal to lambda I times identity matrix times lambda I, right? But I just want you to go through this because this vision can help you to prove other things in the future. It will be useful. Okay, so the whole thing, it is very simple, and actually, you probably might know that already. So basically, what I'm trying to say is lambda A times lambda I equals to lambda I, right? This is just identity matrix. So, which means A minus lambda I times the identity matrix times lambda I equals to 0. Right? So if you are familiar with matrix, familiar with linear algebra, these are just to show you. I try to bring you to somewhere not really related, but hope you can get used to all this notation. All I want to say is just, which is you already know. A matrix times its eigenvector equal to eigenvalue times the identity matrix times the eigenvector. And then I can move this to the left and use distribution law. Then I have A minus lambda I times times lambda I vector equal to 0. Can I omit this capital I here? Why? Because what? Because A is a matrix. You cannot have matrix minus scalar, right? But very often in the literature or when people do presentation, they are a little bit not that rigorous. They just write A minus a scalar number. Sometimes then you should understand it means the scalar times identity matrix. Okay, so be careful of this, right? But here we try to be complete. It's a lambda I times I. Okay, yeah. It won't. Here it just state, given a matrix like this, minus lambda I times this eigenvector needs to be 0. Okay, it won't. I will show you later, right? On the left part, yeah, it doesn't need to be, right? Because it's just saying that so he tries to say that if this is diagonal, does this need to be diagonal? It doesn't have to, because here the matrix is many elements. It doesn't need to have one-to-one correspondence. The net result is that this matrix, try to rotate this vector, is the same as just applying a scalar to it. Let me give you an example. For example, what we learned about sigma y, right? 0, negative I. This is not a diagonal matrix, right? And if you apply to its eigenvector 1i, is just equal to 1 times 1i. We learned this, last time we diagonalized it, remember? Yeah. So this is A. This is lambda I. Right? So they don't have to. Why? Because to get this element, you actually is a multiplication and then summation. Right? So I don't need to be the same. Okay. Now, then this involves a system of linear equation, because the trivial solution for this one is that lambda I equals 0. The 0 vector, everything is 0. Remember, I talked about this 0 vector, everything is 0. Then it's a solution. But that is a boring, trivial solution, right? And the theory tells us that if you want to get non-trivial solution, here you just take it for granted if you forgot what you have learned before or in other places. This just tells us that the determinant of this ones, the matrix needs to be 0 to have non-trivial solution, or non-trivial lambda I, right? Non-trivial means that it is not equal to 0 vector. Everything is 0. Okay, so we did not do a lot. The whole main point in this slide is just that I want to tell you that if you have the eigenvector or eigenvalue, you come with this equation. And in order to find them, in order to have non-trivial solution, you need the determinant A minus lambda I times identity matrix equal to 0. Okay? And then we can use this to find the eigenvalue. Okay? So let's try that, right? We'll try that later, sorry. I still want to say one more thing. Yeah. Yes. No. Hermitian matrix just require that is adjoint equal to its own, right? For example, this is Hermitian. So you see that it can have complex elements. Yeah, but its eigenvalue is going to be real. Okay. So there is one thing. And second thing I want to mention is that what if we represent the matrix in the basis formed by its eigenvector? So this is a little confusing. What does it mean? For example, y has this eigenvector, but we write this in what basis at this moment? Basically, what is the meaning of 1 and I? One part of what? Do you remember? 0. And I part of 1. I mean, it has, right? Because this means it is 0 plus I1. That is the meaning of this. And that is the basis we have been using, 0, 1 basis. We call it computational basis. Just any basis you start with. Okay? Now, but what if I express everything in the basis of the eigenvector? Means now this itself is a basis vector. Okay, and it has another eigenvector that become another basis. And what we learned before is just like the plus minus, remember, for the sigma x, right? So we need example to understand better, but just here, just pay attention. We represent the matrix in the basis formed by its eigenvector, right? For example, sigma x uses plus minus instead of 0, 1. Do you see what I'm trying to say? Right? So for now, I try to express the space using plus minus basis instead of 0, 1 basis for sigma x. Okay? So I'm talking about what happens if that is the case. Okay? So this is what we know. If lambda I is an eigenvector of A, and again, what does it mean? It means A applied to lambda I equals to lambda I, lambda I. Okay? And if, right, A is n by n, or in other words, this is an n-dimensional space. Then A has n eigenvectors. Okay, so this is given, we did not prove, but I hope you can appreciate, right? If n by n, you have n eigenvectors. And we are going to call them 0. I actually will call it this. I'll call it lambda 0, lambda 1, and all the way to lambda n minus 1, which is the same as saying 0, 1, all the way to n minus 1. Is this okay? Can I say that? Can I say that now I relabel my eigenvector as 0 to n minus 1? Just relabel. We can change our name, the whole class. Let's change our name tonight, right? Everyone just add maybe sir in front of it or madam in front of it. We still ourselves, we just relabel our name, right? So because the cat, again, everything inside is just the name. As long as we define it and we agree on it, then we can call it anything. So this 0 is just lambda 0. N minus 1 is just lambda n minus 1. Okay, so what I'm trying to say, okay, A has m eigenvector, and these are what they are, right? Then if use, right, lambda use a basis formed by I call it I. Why? It means I equal to 0 to n minus 1. What we're trying to say is we use the basis formed by the eigenvector of A. Then we don't prove it. Then A is going to be lambda 0, lambda 1, all the way to lambda n minus 1. And everything is 0. So maybe no one asked me, but when we see this, it means that all elements are 0 in this triangular corner. And we have diagonal value lambda 1, lambda 0, lambda 1, all the way to lambda n minus 1. So what does it mean? It says if you use the eigenvector as the basis, then that matrix is going to be diagonalized with its eigenvalues. Might not make, I don't know, I'm not asking if you make sense or if you can prove it, but do you understand what I'm talking about? Okay, you use its the basis as the, its eigenvector as the basis, then you have a diagonal matrix. And the diagonal elements are their eigenvalues. So you see that diagonalizing a matrix, we will look at it again in the future, but this is a very important problem, very important engineering problem. You can diagonalize a matrix. It's just equivalent to find its eigenvalues and eigenvector. In almost every engineering problem, you solve differential equation. The goal is to diagonalize a very big matrix. If you can diagonalize it, you find the solution of many important problems. Okay, yeah, question?
So should the lambda pixel set constant multiple number?
Constant multiple?
Because you say that A lambda is equal to some constant times lambda I.
Yes. Yeah. You don't have to. So when we say A times this vector is equal to a number times that vector, this number is the eigenvalue, this is the eigenvector. And that's it. And then we say we form the basis by using this eigenvector. And with that, A can be represented by this diagonal matrix with the eigenvalue along the line. Okay? Now, I did not prove it, right? But we can check to see if what we are, this is something very useful, right? Sometimes to check if you are getting a right equation. It is not proving, it's just checking. So what can we do? Why don't we check the definition, right? So when we write this guy, when we write the eigenvector we use the eigenvector as the basis vector. Now we write it in column form. How would it look like? Maybe it's difficult to see, right? How about let's start with this. How would lambda 0, which is 0, look like? 1, 0, 0, 0. Exactly, we have n dimension. Why is that? Because remember what we talked about this column form? This refers to the first eigenvector, this first basis vector. This is the second basis vector. This is n-1 basis vector, right? And we just say that we are using the eigenvector as the basis. Then the eigenvector itself must be one of these, right? Or you go back to 0 and 1. How do we write 0 in column form? 1, 0. Because we're using 0 and 1 as basis, right? This is confusing. Let me show you here. For example, in the 0 and 1 basis, how do you write 0? We say this is 1, 0. Why you agree? Because this refers to I have one part of 0 and one part of 1. How about what is 1? 0, 1. This refers to 0 part of 0 and 1 part of 1, right? So same here. I'm saying that I already used this eigenvector as the basis. Then, of course, my first eigenvector must be one part of the first one, right? Second one will be lambda I, which is I, must be equals to 0, 0 all the way, and then I have a 1, and then the rest is 0, and this is the ith row. Make sense? I know this is very confusing, so I hope that you can go back to read it and try it. Use some numerical example, and then you will see what it means, right? So now, because of this, let me just quickly show that A times lambda I is nothing but, because it's diagonal now, lambda 0 all the way to lambda I, and then all the way to lambda n minus 1, the whole thing times 0. And then at the ith row, I have 1. Again, this is ith. This is the ith row. Do you see that? So this is lambda 0, and then the rest is 0. When I multiply this one, what do I get? This row times this column, what do I get? This column, this row times this column, 0. Because lambda 0 times 0 is 0. The rest is 0, so they are all 0, right? Until I reach the ith element, what do I get? This 0 here, all 0, but lambda I will times 1. And then the rest is 0 and then times 0, right? So the whole thing will give me 0 lambda I 0. Again, this is ith. Correct?
Yeah.
And then I can factorize lambda I out. Then this becomes 0, 1. But of course, this is just equal to I. Correct? So lambda A times lambda I cat is equal to lambda I times, just to be complete, I should use lambda I instead of I, so you won't get confused. So what do we learn here? Just this. If you express the matrix in the basis formed by the eigenvector, then the matrix is just a diagonal matrix with the eigenvalues. Okay, so again, we did not prove anything. It's just practicing. And that's why some people ask me, what do I need to study for the exam? The most important is you understand every step here. If you understand with no confusion, then you are good for this part. And the rest is what? Copy this in cheat sheet. You understand what you have copied. Right? So remember, if I represent in the use the eigenvector of a matrix as the basis, then the matrix can be represented as a diagonal matrix. Now, I know it's not easy, but let's do an example. So let's consider sigma x. Do anyone remember what is the matrix element of sigma x? 0, 1, 1, 0. Good. When I write this from now on, you should know what basis you are using. Okay? What basis are we using? Do you know?
0, 1.
Yeah. This is in the 0, 1. Maybe I should not. This is confusing. Let me just call it 0, 1 basis. Okay? No, but the first thing what I want to is to diagonalize this matrix. I want to find eigenvalue, okay? So diagonalize. The so-called diagonalize is equivalent to finding the eigenvalue. And I'm using the method we just used. What did we say? A minus lambda I equal to 0. That is the equation we say here. A minus lambda I equals 0, but now A equal to sigma x, right? Okay, so is it this difficult? Sometimes you think it's difficult, but it's very easy in quantum computing for 1 qubit because it's just 2-dimensional. All you need to do, just do it step by step. Okay, like my book, 0, 1, 1, 0 minus lambda, what is I? 1, 0, 0, 1. Okay, do matrix operation. What is this? 0 minus lambda, 1. 1. 0 minus lambda. Am I right? Maybe I just take away 0. I don't want to do another 9. Am I right? Anyone has questions? Do I do it correctly? All you need to do is element by element. First lambda go in. Lambda times 0 is still 0. 0 minus lambda. 1 minus 0. 1 minus 0. 0 minus lambda. So I got negative lambda, 1, 1 negative lambda. Right? And I say this one need to be 0. Do you remember how to find the determinant? Some of you might forgot, right? Diagonal down, multiplication, and then minus the other way, right? So it means I would write down the step. Negative lambda times negative lambda minus 1 times 1 equals to 0. That's the equation we need to solve, which means lambda squared minus 1 equal to 0. So what is lambda? Plus 1 or minus 1. I'm done. I'm done with the diagonalize. I did not diagonalize it, yes, but I'm done with the eigenvalue, right? It has 1 or minus 1. Now, without proving it, do I need to show you how to? Okay, let me just go ahead. I actually want to then continue. Now, find the eigenvector. Now, if you want to find the eigenvector, remember last time we tried to find eigenvector first and then eigenvalue, right? Use the matrix, just equating the element in the matrix. This time using determinants, I find the eigenvalue first. To find eigenvalue, we just take an example. For example, let's consider lambda 0 equal to 1. This is the first eigenvalue. Then what do we have? We have sigma x lambda 0 vector equal to lambda 0 times lambda 0, right? So sigma x is 0, 1, 1, 0. The eigenvector, we call it AB, equals to 1 times AB. Based on this, then it means BA equals to AB. Right? I just 0, 1 times AB, 0 times A plus 1 times B equal to B. 1 times A, 0 times B equal to A. Then what do we get? What do we get from this equation? I have a vector equal to another vector, then it means what? Thank you. The elements should be the same. A equal to B, right? And then plus you need the normalization condition, but anyway, I would just say that the lambda 0, we want it to be the same, right? As I told you last time, you can multiply by anything, right? Because there are infinite number of solutions. So I just choose 1, 1, right? But I need to normalize it. Then I get lambda 0 equals to 1 over square root 2. Oh. One, 1. And if you remember, this is the plus state. Okay, and do it yourself at home. Okay, find lambda 1 for lambda 1 equal to negative 1. And you should know what it is, right? Anyone remember what is the eigenvector correspond to eigenvalue of negative 1? Or the other eigenvector? Thank you. 1 by root 2, 1 minus 1. So please go back to try it. Right? It should be, answer is negative. Okay. Any questions? Now, so I spent a lot of time. You did not learn much. The only thing you have learned really is that to find the eigenvector, eigenvalue, we can use this equation, determinant. And we also know that if we write in the basis form by its eigenvector is diagonalized. So we know that you find the eigenvalue, you diagonalize the matrix. But more importantly, we've gone through a lot of examples, right? Not just that when I write its example, then it is an example. Even for this, all my slides are example. I try to go through the math with you, so you need to understand that. Right, these are your exercise, yes. It doesn't, does diagonalization need to be on orthonormal basis? Normal matrices, yes, yeah. Normal, but there's a definition of normal matrices is that A dagger equals to square root or what? What is the definition? I forgot. Equal A dagger A. Okay, it's something called normal matrices. Thank you. Not talking about the vector being normalized, but there's a definition of a matrix if it can be decomposed, right? Decomposed into, let's say, A dagger A equal to A dagger, then it is normal. Yeah. It's just a special definition. Yeah. So it doesn't need to be awful, but I cannot answer. Sorry. So maybe we should ask ChatGPT. Yeah. So good thing is in quantum computing, just everything is orthonormal. Okay. Okay. Now then we can represent x in the basis form by itself, right? So we don't prove it, but now based on what we just said, we say sigma x equals to 0, 1, 1, 0. This is in 0, 1 basis. Right? But what if I write it in the sigma x eigenvector basis? And we actually have shown that if they are plus and minus, what would they be? Based on what we just said. It's going to be what? First of all, if you write it in its eigenvector basis, what happened to the matrix? Diagonal, yes. So it means 0, 0. Right? And then what would be the elements along the diagonal? They are their eigenvalues. What are their eigenvalues? Plus 1 and minus 1, right? So this one look like what? Which matrix? Sigma z. So it's interesting. They actually are equivalent. Sigma z is diagonal because we are writing in 0, 1 basis. 0, 1, the eigenvector of sigma z. And if we write in sigma x basis, then you have the same form. So actually cannot distinguish them. The reason you find sigma x and sigma c difference is just because you write in different bases, right? So none of them are particularly more important than the others, right? It's just like we speak different languages. Just because today we use your language, then my language is called foreign language. But tomorrow you speak my language, your language is foreign language. But the thing we express are exactly the same, just depending how we set the coordinate. Okay? And let me just save the time, right? So just check, right? I ask you to check that what I'm saying is check by working on sigma x eigenvector basis. Okay? Check what? Check sigma x lambda 0 equals to lambda 0, lambda 0, sigma x lambda 1 equals to lambda 1, lambda 1. So actually, maybe I give you some hint, right? So now it is in the sigma x eigenbasis. So when I write it, this is going to be 0. No. What is that? Should be 1, 0, 0, negative 1. This is sigma x. And what is lambda 0 when I write it in the sigma x eigenbasis? Yes, I got it by 1, 1, right? But now this is in the 0 and 1 basis. Now it, in its own basis is what? 1, 0. And this is equal to 1 times 1, 0. Okay, and do this. Right, so I hope you can link this. Now when I say I have 1, what is the meaning of 1 here? 1 part of what? 1 part of 0? Sorry, say again. 1 part of lambda 0 or plus. Yeah, lambda 0 is plus. Very good. Which is equal to 1 over square root 2, 0 plus 1. Okay? It's still 1, 0. But it's 1 part of plus, right? Because it's the basis vector, the eigenvector of segment. Okay, any questions? A lot of math, we're getting more, but later will be a little bit easier. But okay. Now, if I give you the eigenvector and eigenvalue in any basis, I just give you the eigenvector and eigenvalue. How you construct the operator? These are just the rule, and you just need to use it because so I try to show you all the essential linear algebra. Then later you can apply in the quantum algorithm, right? So if you cannot fully derive or understand, it's fine, but you take it as rules. Okay. So let's say given A's eigenvalues. Okay, I tell you, right? And vector. Right? So what are the values? Lambda I, vector will be lambda I cat. Then how do you construct A? A equals to summation J equal to 0 to n minus 1, lambda I, lambda I, lambda I bra. Very confusing. But at this stage, if you cool down, you should not be scared by this, right? Let's just do it slowly. What is a number, vector, or matrix? Matrix, as we said, we're talking about matrix operator, right? It says that it's equal to lambda I. What's lambda I? Scalar. And it is the eigenvalue of A. It's given. We assume it is given. Then what is this guy? The eigenvector, right? This is the eigenvector, right? It's bra or cat. How about this one? Bra. So we have seen bra on the left and cat on the right. That give you what? Give you a scalar. It's an inner product. This is kind of like outer product. You swap them. And what does it give you? It gives you matrix. Maybe you are surprised, but let's look at this. Cat is AB. This is AB. This is bra, right? This is cat, right? This is bra, right? How do you do matrix multiplication? Row times column. Row times column. So it is A times A times B, B times A, B times B. It gives you a matrix. Right? Just a numerical example. Okay, so you agree with me? If you follow the rule, if you cannot follow, then you need to practice. The point is cat times bra give you a matrix. So does it make sense, this equation, first of all? Right? Sometimes I read paper, they are very long equation. By trying to see if this makes sense, I can follow much better. Because when I try to follow, I can see that, oh, this is cat bra, I can convert to matrix, then I have some idea of what's going on. So summation, you understand what it is, right? There's a typo here. What is the typo for this summation? J, right? It should be what? Should be I, right? I might not be wrong, right? You cannot prove that I'm wrong because maybe the equation is just a dummy variable J that you never use, but you're right, it should be I. So what does it mean? Start with I equal to 0, lambda 0, lambda 0, lambda 0, then plus lambda 1, lambda 1, lambda 1, plus lambda 2, lambda 2, lambda 2, all the way to lambda n plus 1, right? For those who forgot. Lambda 0, lambda 0 cat, lambda 0 bra, lambda 0, 1, lambda 0, lambda 1, lambda 1 cat bra, plus all the way to lambda n minus 1, lambda n minus 1 cat, lambda n minus 1 bra. They are very long, but you should be able to understand. Okay, so don't get scared by this. You will see a lot of this equation. All you need to do, just sit down, write it down, think about every term, then you find that you understand very well. What you're trying to say is just, okay, you just form a matrix using your eigenvector, scale it by the eigenvalue, add them together, then it is the matrix that then you get the representation of this matrix. That's all is what you're trying to say. Okay, so let me give you an example. For example, let me tell you, given the eigenvector and values of sigma x b 1 over square root 2, 1, 1 for correspond to plus 1, right? And then 1 over square root 2, 1 minus 1 correspond to negative 1, right? The first one is eigenvector, the second one is eigenvalue. Okay, do you understand what I'm doing here? What I'm giving you? I say that I have a matrix called sigma x. It has eigenvalue plus and minus 1, and its corresponding eigenvector are these two. So what I'm trying to say is, this is lambda 0. This is lambda 0. This is lambda 1 cat. This is lambda 1. Make sense? Any questions? So can you construct sigma x based on the equation? Just follow what we write before. Lambda 0 outer product plus lambda 1 outer product. How about lambda 2? Do I need to add lambda 2 outer product? Why? Because there's only two sets of eigenvalue, eigenvector. But why it only has two? Thank you. It's a two-dimensional space because it's a 2 by 2 matrix. It's given, right? Here, actually, you cannot see it. So I already tell you that what I'm giving you is complete. It's everything. Okay? So, okay, let's do that. Lambda 1 is what? Lambda 0 is what? 1. And then lambda 0 cat is 1 over square root 2, 1, 1. Bra is 1 over square root 2, 1, 1, right? Do you remember how to find the bra? Transpose, rotate, and then compress conjugate. They are real numbers, so I did not apply compress conjugate. What is lambda 1? Thank you, negative 1. And then lambda 1, 1, 1, negative 1 over square root 2, 1, negative 1, right? Are you okay with what I wrote down here? If you can write this down, you should be able to calculate. Right? So this is lambda 0, right? So 1, 1. This is lambda 1, right? So 1, negative 1. Okay? So now let me calculate. I can ignore 1, right? I can take 1 over square root 2, and it is square. I have two of them, so it becomes 1/2, right? So I take this out. And then the first matrix is what? How do you multiply this matrix? I mean, do this outer product. 1 times 1 for the first element, 1 times 1 second, 1 times 1, right? So it's 1, 1, 1, 1. And then the second one, I have a negative, and then I do the multiplication. 1 times 1 is 1, but 1 times negative 1 is negative 1, negative 1, 1, right? So you see this is 1, negative 1, negative 1, 1. You go through the math. 1 minus 1 is 0. 1 minus negative 1 is 2, right? So you will get 1 over 2 times 0, 2, 2, 0, which is 0, 1, 1, 0. This is exactly what we know about sigma x in this 0, 1 basis. This is just to show you how you do it, right? So if this equation is confusing, if you can understand this one, then that will help you. So that's why I always say, if you find some equation you don't understand, try to represent in matrix form. Go through the elements one by one, and then you will understand, and then you can generalize to a higher dimensional space. Okay, any questions? Yeah, a lot of math. A dagger bases, would it be the same? Not necessary. Are you saying that do they have the same eigenvector? You have a good point. Yes, you take dagger, but the point is that you have a complex number here, a complex conjugate for lambda I, right? But yes, but this one you swap it, they are still the same. Cat become bra, bra become cat. Okay. So I need to introduce